There you go.
All right, cool. Thank you. So as Tao said, my name is Renaud. I'm an engineer at Slack on the Search Learning and Intelligence team. We're based out of New York City, and today I'm going to talk about how we build recommender systems with strict privacy boundaries. So I'm first going to talk about data at Slack and how it applies to recommender systems. And in the second part, I'm going to talk about a few techniques we use for dealing with this data through two features we implemented in the product. So, well, someone already stole my question, so we can skip that. So next question, what is Slack really? Is it email? Is it a chat room? At its core, Slack is a communication platform. So for the few of you who haven't raised your hands, this is what it looks like. So it allows users to communicate, so to send messages to each other. And the way they do that is through channels, where these channels represent particular topics or projects, or really anything you want. So there are two things about Slack that kind of makes it a little different from other communication platforms. So the first one is that data is public by default within a team. And here I mean team in the sense of a Slack team, so an organization or a company. And also there are some strict privacy boundaries between teams. So what do I mean by public by default? Well, as opposed to email, when you write an email, you select a set of recipient, and the message only goes to these recipients. In Slack, most communication happens in public channels, and when you send a message to a public channel, that message is associated with the channel. And by virtue of being public, this channel is actually accessible to anyone else on the team. And so that means anyone on the team has access to all of the archive of all conversations that ever happened. This is true even of new users. This is another big difference with something like emails, whereas in email, when you get a new email account, you start with an empty inbox with maybe a welcome message. In the case of Slack, you actually get access to the archive of all conversation that ever happened in Slack. It's a pretty interesting feature. Internally, we can go back to the messages that were first sent by the few founders a couple of years ago. And so this gives us two things. It gives us a huge source of data for building recommender systems, both for training these systems, but also for pulling recommendations from that data. And the other thing is it actually makes recommender system even more valuable, right? One of the main complaints we have from large teams is this issue of information overload. And so recommender systems here are used as a tool to make sure users have access to the data they need to do their work while still keeping some of the noise out. The second characteristic is, like I said, these strict privacy boundaries that exist between teams at Slack. And so data at Slack is strictly segregated by team. If someone says something very secret in Team A in the dogs channel, we really don't want it to leak in Team B. And this does not apply. This does not only apply to explicit leaks, but also to implicit leaks that could happen through our model, right? One of the examples we use for an implicit leaks like this is, let's say we're training a topic model, and we're training it on data on Team A, and Team A is going through some rough time and is talking a lot about layoffs. If the model were to infer an association between A and layoffs and were to reuse that model in Team B, and Team B could basically infer that association back through the users of the product, that would be pretty bad. So we have to be super careful when building recommender systems to make sure we respect these privacy boundaries, both implicitly and explicitly. So in terms of recommender system, this kind of puts Slack somewhere between email and Netflix. So on the email side, you're very restricted in what you can recommend to users. In terms of, in the case of Slack, you have some freedom to recommend things within teams. But as opposed to Netflix, where every item is pretty much fair game for any user, we really have to respect these team boundaries. So what are some of the techniques we use to solve this problem? So I'm first going to look at a feature we built called channel recommendations. This is pretty much your typical recommender system problem. So we have a set of users, and we want to recommend them channels based on the channels they are active in. This is what the feature looks like on the right. So in this case, it's a bot that recommends to the user a set of channels we think might be interesting to that user. So the way we model this, we build a user channel activity matrix. In this case, the known items in that matrix are computed from the user's activity in this channel, so reads and writes activity. The light green are the unknowns, and all of the white is the off limit. So basically channels or users that are not in the same team and that we don't want to recommend back to the user. Just to give you an idea of what kind of data we're playing with, we have over 8 million daily active users. We have around as many channels. We have over 500,000 teams, so we have over 500,000 of these like small clusters along the matrix diagonal. And team varies widely in size, right? We have teams that have only a few users, and our biggest teams have tens of thousands of users. So the technique we use to solve that is actually pretty old. It was published 17 years ago. It's not the latest and greatest. It's not deep in any way. It's this thing called item-based collaborative filtering. And the reason, so just give you a refresher of what this does. So we first start by computing a channel similarity matrix. The way we do that is we compute the cosine similarity between every pair of channels. And then when we want to recommend channels to a user, we look up what channel the user is active in. We look up the rows for these channels in the channel similarity matrix, and then we do a weighted sum to get a list of channels to recommend. So why does this work really well for us? The first reason is locality. Although we're learning a global model, we're actually at the same time kind of learning a bunch of small individual models. And the reason for that is the cosine similarity, by definition, is guaranteed to be 0 between channels on different teams. And this is because there's actually no overlap in users for channel on different teams. So we don't have to worry about leaking data between teams. It's also pretty neat in terms of performance. We can, this locality is actually something we want, since we want to be able to recommend channels for teams of all sizes, including small teams. It's also very scalable. So as I said, we run this as one job. So this is only one job we have to monitor. We don't have to monitor 500,000 jobs. We don't have to tweak 500,000 jobs. We have only one. So this is a great thing from an operational perspective. And we can actually exploit the team boundaries in our data to make this a little bit more efficient. So instead of having to compute O of n square cosine similarity between pairs of channels, we can join on team and only compare channels within the same team. And so this reduces the number of computation from O of n squared to O of km squared, where m is much smaller than n. In this case, m being the size of the largest team and k the number of teams. In reality, it's actually much faster than that, since the majority of teams are much smaller than the largest team. And so that's why we picked this, even though it's old. It works pretty well for our use case, given our data. The second feature I'm going to talk is called highlights. In this case, we want to recommend to users the most important messages they should read based on their past activity. So this is what the feature looks like on the right. So we have a list of 10 messages that we think the user should look into. The way we compute this is with an engagement model. So we use engagement as a proxy for importance, and we're basically trying to figure out, try to build a model that predicts how likely is a user to engage with a given message. And then we can recommend to the user the 10 messages they are most likely to engage with. Again, we have 8 million daily active users, 500,000 teams. We have over 200 million public messages sent per week. So that's our kind of candidate set. And the engagements we're tracking in this case are clicks, so clicks on files, links, as well as reactions and replies. Reaction in this case being the little emoji you can add to a message. And the way we do this to preserve privacy is by learning global model trained on parameterized attributes of user and message. So I'm going to go into more details about these different terms, but this is a technique that draws heavily from a paper that was published by a few folks at Google for email search. So the reason we're learning a global model here instead of a bunch of a local model is because team data is actually too sparse. If you do some back of the envelope math, you quickly realize that assuming something like a 1% engagement rate, which is usually around what we see for clicks, reactions, and replies, we get around 60 engagements per week per team. That's not a lot. On the other side, if we pull all of the data for all the teams together, we have around 30 million. So that's more than enough to learn a good model. And the way we, like I said, the way we guarantee privacy while still training a global model is through these parameterized attributes. So what do I mean by this? Well, let's look at a message. So this is a message. It has some text, a file, a reaction. And from this message, we can extract attributes. So we can kind of project the message into this attribute space, where attributes are kind of multidimensional features of the message. The reason we don't want to feed this directly into our model is twofold. First of all, these are very sparse. There's not that many messages with a given user ID, author ID. There's not that many with a certain set of reactors. And also, we don't want to leak private data, right? If we use words as an attribute, we don't want to feed words directly into our model because there's a danger that the model will start to learn some correlation between words that are going to leak to other teams. So the way we get around this is by taking these kind of high-dimensional attributes and we parameterize them. So basically, we compute function of these attributes that are one-dimensional and real-valued and generalized to every team. So in this case, for example, we have this attribute that's reactor IDs, so the list of users who reacted to a message. We don't want to feed that directly into the model, so what we do is we compute a function of that that's just the number of reactors. We lose some information, but in this case, we're making sure we're not leaking any information, private information into the model. Since num reactors is more or less, doesn't say anything about the person who actually reacted to the message. And so in this way, by feeding something like just asFile equals 1 and num reactors equal 1 to the model, we don't leak any private information to the model. But in this case, we have this problem now that there's no personalization, right? If we only use features of the message, everybody's going to have the same experience, and that's not what we want. And so let's add a user. Like the messages, users have attributes, so we can project the user the same way we do with the message into this attribute space. Once we have both in this attribute space, we can compute features. We can, again, parameterize these attributes by computing features that are function of both a user attribute and a message attribute. So we take, again, these two I-dimensional attributes, and then we combine them into a single one-dimensional real-valued feature that factors out the private information. So that factors out the user ID and the author ID. In this case, one of the most common features we have are these kind of CTR or engagement rate features. So we will look at all impressions that we've logged over the past 6 months, and then we will look at all the impressions where the user has a certain attribute and the message has a certain attribute, and then we'll compute the ratio of how many of these impressions were clicked divided by a total number of impressions. So basically, in other words, this is the CTR for when the user has this user ID and the message has this author ID. And so by feeding this into the model, so this feature, instead of feeding the high-level attributes, we actually don't leak any private information into the model, right? There's nothing in user author CTR equals 0.1 that tells you anything about the user or the message, so we're not at risk of having the model leak some information. And we repeat that for a bunch of different attributes. On the user side, we have the user ID, we have the team ID, we have channels we think are important to the user, and then on the message side, we have a bunch other ones, the author ID, the channel ID, the words, the reactors, the clickers. And so this allows us to generate a bunch of interaction features that are good from a privacy standpoint. And just to recap, so in this case, going back to the original diagram for the model, this kind of layer, this feature layer, allows us to isolate the privacy-sensitive user attributes and message attributes from the model, and so we can reuse the model across different teams. So this is it. Thanks for listening, and I guess let me know if you have any questions.
Hi, Marina Karpusha from Amazon. I have a question. So if I understand correctly, you try to identify the data that is private and should be used in the recommendation, building your recommendation, right?
Sorry, I couldn't hear.
So you try to identify private features
Yeah.
of the user and not use into the recommendations.
Yeah, correct.
Did you consider to use any ML models that just try to guarantee differential privacy and using this data?
No, we haven't looked into differential privacy. The main reason is I'd say differential privacy is harder, and it's something not only that's hard to get right, but if you don't get it right, it's completely useless. So we want to look into it in the future, but we haven't looked into it right now.
Peter Gorniak, DeviantArt. I'm wondering about the signals you're using from your users, because Slack seems to me it's a little bit different from other cases where you watch a movie and you enjoyed it. How have you done studies on how good your recommendations are and how users perceive them? I mean, maybe you can't share this, but I could imagine that a lot of people react to messages that are not the ones they want to be alerted about.
Yeah, so we've done a mix of things. We've done user studies where we've had users go through the feature and kind of like tell the interviewer, is this a good recommendation or not? But also there's a feedback mechanism included in the feature. So there's a kind of a thumbs up, thumbs down. There are thumbs up, thumbs down buttons, so you can click those to see. And so we get a significant number of those. And so we've been using that as kind of another way of evaluating the model that also evaluates our assumption that engagement is a good proxy for importance. That being said, we're still, it's definitely like an open question as to what's the best combination of engagements and the right value for different engagements.
Hey, I'm Pierre from the European Broadcasting Union. What's the point of using words to define the attributes of the messages? What does it tell you about messages?
The words?
The words, yeah.
I mean, in this case, users might be more interested in messages that contain certain words. So that's what we're trying to capture is with using words. Did I understand?
Well, I wasn't sure, but whether you were looking for certain words or whether you were looking for the number of words, that doesn't...
Yeah, sorry. So we have a number of features. I mean, the number of words is definitely something that's predictive of messages being higher quality generally, so users tend to be more interested in those. But also particular users might be interested in particular words. So these are kind of two ways we can integrate that into our model.
Thanks.
Okay, let's thank the speaker.
Thank you.